All right, thank you very much. Yeah, for those of you who haven't met me so far, I'm Cameron. I'm a postdoc at Caltech. And yeah, I'll talk about simulations, something we haven't heard a huge amount of so far because there's a limited simulation community that's represented at the meeting. So we've heard a lot of really great talks about a variety of different Python packages that people have been developing together or developing individually. But for a second, I want to take a step back from that and talk about how we envision things being best for the community and what we can do as a whole to make the community better. I think a lot of what's been done by people involved in this community so far is great. The AstroPy stuff is great, but specifically I'm looking more at the simulation side of things. So, okay, so pause there. Simulations, as we all know, are very useful for understanding physical phenomena. By taking observations of something where we don't necessarily understand what we're doing or what's going on there, if we can't analytically solve the equations associated with that physical phenomena, we can model it numerically and try and provide some context for understanding the observations of whatever we're looking at. The problem is in trying to compare these simulations against observations that we originally had to justify doing the simulations. Because the simulations contain a huge amount of information in them, and trying to condense that down can be really difficult. So, as an example, here is a cosmological hydrodynamic simulation of a big representative volume of the universe, looking at gas density over redshift from redshift of 100 down to 0 over the course of the evolution of the universe. And you can see a lot of structure that's forming. In this particular simulation, we have like 100 million resolution elements. And each of those resolution elements has density, temperature, a variety of fluid quantities, as well as velocity of the gas. It's a huge amount of information. A single snapshot's like 100 terabytes. I'm sorry, not 100 terabytes, 100 gigabytes. That would be a lot. That'd be amazing. 100 gigabytes. So this is a huge amount of information. And how do we take this and somehow compare it with observations, which are very data dense, but much more condensed? How do we do that? And similarly, how do we even compare simulations against each other when they use different formats, they use different methodologies, they use different representations of how that data appears in the format? It's challenging. So what I'd like to propose is, how do we compare observations to simulations coming from a variety of different formats and assumptions? What I'd like to propose is that astronomy's lingua franca is observational data. That's what we have from the observations. That's what nature gives us. So we have to convert our simulations to be in that format so that we can readily compare apples to apples. And furthermore, it enables us to make comparisons between two different simulation codes, maybe an SPH particle-based code and a grid-based code, where there are different assumptions going into that are hard to compare against each other, but if we condense them both down to observational data, we can readily compare the two data sets. So, as a community, and I mean this, both the simulation community, more the simulation community, but also the observer community, because we can apply observational data analysis products to these, or data analysis suites to these now synthetic observational data products. We need to produce synthetic observations, whether it be photometry, spectra, IFU data, something like what we see when we look up in the sky and record data. So condense our simulations to observational data. We need to create, and I realize I'm preaching to the choir here, we need to create open source universal codes for generating these sorts of data products. I've listed YT here. YT obviously works on this. I know we haven't talked a lot about YT. Nathan and I might lead a session later today or tomorrow on YT, which is just to give you, for those of you who haven't heard the name, it's a method for, it's a simulations analysis suite, data analysis suite that you can use, akin to AstroPy, but more with the focus on simulation outputs. So, but really the benefit of doing this in the open and having universal codes that can operate on multiple different data formats is that not only are we saving person hours of not having, person X developing their own analysis tools and person Y developing the same analysis tools that might have different assumptions, but we're saving all that time, and it's beneficial to the community to have something open source because everyone can check the methods and make sure it's okay. I think I don't need to go too much into the benefits of open source here. But furthermore, when an observer wants to take an image of the sky, they don't build a telescope to do that. They become part of a consortium that already has access to a telescope, and then they use that resource for their benefit. Similarly, the simulation community in generating synthetic observations should follow that model. And finally, we need to provide open locations for storing these simulated observable data products in the same way that the observational community has archived data, legacy data locations, whether it's Sloan or MAST or that sort of thing. Simulated synthetic observational data products should be able to be stored so that they're accessible by the public. There are a handful of projects that can do this. Illustris, Millennium, Eagles. They can store their data products in the cloud, allow people to download them and use them, but those are big projects with a lot of resources, and some small community, a small group at a university might not have the capacity to do that. And furthermore, if every group had their own archive that was storing their data products, it's a heterogeneous data set. How do you access all of these things from a variety of different databases? It just becomes a mess. So we really need a single or a handful of locations where we can store the data products from these simulations. I'm not saying the simulation outputs themselves because those are far too massive and unwieldy, but I mean these condensed synthetic observable products. Okay, so these kind of three guidelines, I can't solve all of them, but there's some efforts called Trident and MISTY that I'm about to showcase that try to apply solving these principles to the small subfield of CGM, IGM, circumgalactic medium and intergalactic medium. Okay, so just as a brief sidestep, the CGM is called the circumgalactic medium, the IGM is the intergalactic medium, and as their name suggests, it's the medium, the gas that surrounds a galaxy and the gas that's in between galaxies, that's feeding galaxies. Similar to the movie that I showcased before, it's these filamentary structures and the structures in between that are the IGM, and then where the filaments intersect is generally where you find structures like galaxies and the circumgalactic medium that goes around them. Now, it would be nice if we could observe these things directly, but the problem is that this gas is very, very low density, and it's so low density that it's very difficult to detect an emission. So you can't just take a picture of the circumgalactic medium or the intergalactic medium. You have to rely on background objects, primarily bright quasars, bright galaxies, and look at their spectra to pick up intervening material. So here I have a cartoon of a quasar spectrum here as it's emitted, and then in the sight line that passes through some of this circumgalactic medium, you start picking up individual absorption features which indicate what the gas phase might be and the gas column density might be in between that object and the observer. Typical lines that are picked up are Lyman alpha absorption, magnesium 2, carbon 4, and so on and so forth. But each of these, because these different transitions have different ionization potentials, they reveal the phase of the gas, the temperature and the density of the gas that they're absorbing, that are associated with those absorption features. So if you see oxygen 6, which is very energetic ionization potential, it indicates that the gas that's represented for in that trough, that absorption feature, is very hot. Whereas Lyman alpha, potentially much cooler. The problem, of course, is that we don't have an infinite number of quasars out there or background sources that we can readily probe structures spatially. It's up to random chance if whether or not there's a quasar behind the object that we want to look at. So a galaxy, at best, might have one background source so that we can probe one sightline through that cloud. That's a lot less than we'd like. We'd like to see the entire spatial distribution of that cloud and what the phase and density and all of these different quantities are associated with this medium, but we just get a single sight line. Not great. But it means that simulations can, remember that simulation volume that we had, and we had all this information. Well, that's both a benefit as well as a hindrance. It's a hindrance because it's hard to coalesce into some structure we can compare against the observations. But it's a benefit because we have all that information, so we can prepare as many sight lines as we want from the IGM or any kind of circumgalactic medium structure. We can send these sight lines through and generate these synthetic spectra so that we can better understand the spectra that we do have from telescope data. And so, yeah, we forward model the synthetic observations as opposed to taking the observations and trying to back model what configuration of gas produced those observations. So I'd like to now get to the stage where I present my Python project. This code called Trident. It's a universal method for generating synthetic spectra from simulation outputs. This is an example of one of the outputs taken from the Agora simulation suite of a damp Lyman alpha absorber and some of the different metal lines associated with it. I'd like to highlight my collaborators on this, Britton Smith at Edinburgh and Devin Sylvia at Michigan State, who were the name Trident just came up because there were 3 of us. We're pretty unimaginative. So we have a paper coming out soon, and basic methodology behind this is you take your simulation volume here. I've represented it as a grid of gas cells, but this works equally well if you use an SPH method like Gadget, where you're representing the gas as individual parcels. Basically, we take each gas parcel, we take the density, its temperature, and its metallicity, and we plug that into a cloudy model to assume collisional ionization equilibrium, as well as photoionization from a UV metagalactic background at that redshift. And then that gives us what the ionization state for each of the individual ions are in that simulation. So this might have so much H1, and it might have so much O6, and it might have so much neon 8, or so on and so forth. Then once we do that, we can do a variety of things. One, we can make visual representations of what it would look like spatially. So the gas density of a galaxy, what it would look like in H1 or O6 or carbon-4. But furthermore, we can run sight lines through this data, and every time we intersect a certain column of gas in a particular ionization state, we can apply a Voigt profile to our absorption line spectra, and then redshift that according to the line of sight, which dictates the cosmological redshift, as well as the peculiar velocity that dictates the Doppler redshift. So let's just see, I'll show you in a moment an example of this, but it supports basically any arbitrary metal ion species from hydrogen to zinc. It supports any line lists that you want to give it to it, but it has a variety of defaults. You can apply line spread functions and spectral resolutions of common observational tools like COS or HiRes or Sloan spectrograph, that sort of thing. And because it's built on top of YT, it basically will work on any simulation outputs from any of the major astrophysical codes used today, whether it's Gadget or ENSO or Ramses. It should work with everything so that we can compare different outputs against each other. So here's an example of it working. This is a slice, a two-dimensional slice of a galaxy simulation. This is an edge-on galaxy in the middle. Doesn't really look like a galaxy, but that's because, again, this is a slice, not a projection where you can see all the structure of the galaxy. What's that? Yes, well, I hadn't seen the talk from today, so how could I do this at the last minute? You can see the black arrows represent the velocity vectors of the gas that's falling onto it, and let's just pass a sight line through this. So what we're looking at here is the density. I just arbitrarily chose silicon-2. How much silicon-2 is this passing through as it traverses the volume? And then what's the line of sight velocity? This is red shifted, this is blue shifted relative to that line of sight. And finally, this is what the spectrum of the silicon-2 feature, zoomed in on the silicon-2 feature, looks like as we pass through this material. And you can see that it's being built up here. It's red shifted, so it's not right on the 1260 angstrom feature, but you can see the buildup of the spectrum as we pass through these structures. Similarly, let's look at another application of Trident. the buildup of the Lyman alpha forest. So this is a better color map. And what we're going to look at is the time evolution of this box. This is not a great simulation for doing this, but it's showing proof of concept. It's a cosmological box. We're sending sightline through it. And when the observers look at distant objects, they're not just looking at the stuff around the galaxy in particular. They're looking at that entire column from us to it. So we have to model this appropriately. So we'll pretend that this is our background quasar, and then we'll start sending a sightline out through the volume. Now, once we traverse the volume once, we step forward with our time step of our simulation box to the next time step and send the sightline through. So it's a continuous sightline that's going through our simulation volume. We choose a random location in each output so as to not probe the same cosmological structures, so you lose some continua from that. But what you see is the buildup of the Lyman alpha forest and the Lyman beta forest as we're traversing this volume. And this works for any lines. I just chose Lyman alpha and Lyman beta because it was easy and recognizable, but you can do this with metal lines as well. And finally, another application is in interpreting spectral lines, individual spectral features. This is a cost spectra of the Lyman alpha feature at redshift of 0.1 from Trident, that Trident produced. And these are two sightlines that are very close to each other. They're probing a cosmological filament. Now, if you look at this, like me, I'm a naive simulator, I would assume that this is a narrow feature, so it's a cold gas that we're probing, and this is a broad feature, so it's hot gas that we're probing. But what something like Trident allows us to do is step through this and find out what's really going on that produces these features. So this sightline, this is sightline number 1, the top one. We're actually probing a filament in between two clusters of galaxies. They're like 10 to the 14th solar mass clusters. So this sightline is passing through this filament in between these two structures. And what we can look at is, this is the H1 column here, and this is redshift. So basically it's the path that we're seeing that traverses this data. Now you can see the velocity vectors. This stuff is redshifted because it's pointing away from us, and this stuff is blue shifted because it's pointing towards us, because it's all falling onto that filament. So what that means is that each parcel, each dot here represents a different parcel of gas in our simulation. This stuff, the near stuff, is redshifted, the far stuff is blue shifted, and what that does is it shifts those in redshift space onto the same sort of features that you can see up here now. Now we're in observed wavelength space, which is equivalent to the redshift space. We look at the individual temperature of the absorbers, and then we apply a Voigt profile for each individual absorber, and the superposition of those is the feature that we get out of things. That is the initial noisy feature that we saw initially. But we can look and see, oh, well, this feature is actually caused by all these parcels of gas. These parcels of gas sit at about 10 to the 5th Kelvin. It's not really that cold. Similarly, if we look at this broad feature now, we can do the exact same analysis. Again, it's a sightline that's passing through a filament, but now there's more material in the outskirts. And so we have all of this column of gas along that, again, red shifted as it's flowing into the filament and blue shifted as it's flowing into the filament. And that effect concentrates all of those absorbers in the observed wavelength space, which we see up here. And now we see that that broad feature is actually the superposition of lots of cold gas. This is 10 to the 4th Kelvin gas. And it appears like a broad feature, but it's actually just a collection of cold features that are Doppler shifted onto each other, as you can see here. So, I'm just naively calling this spectral deception, but you get the idea that we can do this sort of analysis now where we never could do that before using Trident. And lastly, MISTY is a project PI'd by Molly Peebles at Space Telescope that I'm involved with, that's essentially trying to use Trident to have a direct pipeline to a mast-like interface, so you can store these synthetic data products that are produced by Trident in the cloud, so that people, both simulators and observers, can access this and use them for their own study. A quick pictorial of how that works, but you get the idea. So, thank you.
in terms of scaling upward, what is your vision for how this might scale in the future to broader astrophysical problems?
That's a good question. So, at least on the archival side, so MISTY, this effort to store the data at MAST for synthetic data products, that can easily be applied to larger fields than just the absorption line, IGM and CGM fields, because it's setting up an interface that people, and a storage space that people can use. In terms of other simulated observable data product codes, I think YT provides a good basis because it can read in simulation outputs from a variety of different codes, and it just requires different ways of converting those simulation data into observables, whether it be radiative transfer to get full photometry images. There's talk of potentially using Tom Robitaille's Hyperion code to do this, but yeah, we wanted to do it for our community and hopefully provide a model for how this can be done by other.
Thank our speaker again.